Hello, calculus students. I hope you're doing well. We are about ready to start our new chapter, chapter 4 on multivariable functions. Okay, and you may think that, hey, we've had multivariable functions already. The type of functions we studied in the previous chapter is called the vector valued functions, right? You had one parameter t usually called, and then the range was in R2 or R3. Well, this time you kind of reverse the domain and the range, and that's what we call multivariable or multi-dimensional functions. And so we'll be studying these, and section 1 of chapter 4 is the basics of these multivariable functions. So let's get started in our first section on multivariable functions. Okay, so section 4.1 starts multivariable functions, right? And so we have had different types of functions. Here's the first type of functions. For many, well, let me just talk about what a function is, okay? And I've done this recently, but I think it's worth remembering this, right? So what is a function? In general, I mean, at the beginning, you know, when you learned about functions, function is just like a box F that takes on a number X and spits out a specific number Y, which is a unique output for each X, right? And so Y is the output of X as X is passed through the specific box F, and Y is called F of X. X is called the input value, Y is called the output value, okay? It was great, all right? And that's exactly what a function is, all right? A function is a relation in which for each X in the domain is the set of all input values. There is one specific one and only one specific value Y, which is the output for the input value X. Okay, great. And so first X and Y were both numbers, namely real numbers. Okay, and so for many years, this is the only type of functions you study. And this is a real valued function on the reals. Okay, we talked about this before. We have this X value, Y value. If the function is continuous, you'll have a continuous graph like this. And so, you know, we had many examples. In the previous section, we also talked about a function like this where you have f of t is equal to some vector in 2 or 3-dimensional space. And so if you assume it's the 3-dimensional space, you had xt, yt, and zt. These are called VVF, vector valued functions. Okay, so we mentioned and we studied these, and these are great in describing things like the motion in space and so on. Okay, so here's what is new in this chapter. This time we start with a domain of R2 or R3 or some subset of thereof, and then that is going to give us a real number. Okay, so in both of these, the important thing is these are real valued functions. Okay, the values, the codomain is a set of real values. So these are real valued functions. But the difference is it's not just on the reals, okay? It is defined on either the pair, ordered pair, or ordered triple, right? So, so here in this case, for instance, you may have f of x, y is, you know, some function which is z, okay? And it could be, again, it's a real valued function, so z is a real value. Or f of x, y, z can be some real number. Now, we have already used x, y, and z, and that is the end of our alphabet. So we can go back and call it w or something. So let's think about this one specifically. The idea here is now you have a domain, which is either the subset or the entire, well, the subset of R2. And so for each value x, y, there is a specific value of z that's defined. Okay, so the graph of these functions, this new type of function, the vector, the real valued functions, but multivariable functions, will be something like this. Okay, so the z value represents, the z coordinate represents the function, the value of the function f of xy. Now this, if you have the domain that's a three-dimensional, a subset of the three-dimensional space, then it's more difficult. And in fact, it is impossible to graph, right? Why? Because as you can see, if you have the domain that's two-dimensional and the codomain or the range is one-dimensional, altogether it's required that you have three dimensions. So to graph this one, you have to have a fourth dimension, which is really, really hard for us to visualize. All right, so what are we going to do with these? Okay, we will see the first, we will evaluate this. That's not hard to do, evaluate. Okay, we'll talk about the domain, which is the natural domain. We'll talk about the range, because the range is a subset of R, not always the entire R. We'll also talk in the next section about the continuity and, of course, its related idea of limit. Okay, but that's not until the second section. We'll be talking about what we know as level curves. Okay, and then traces, which you may be familiar with, because we've done some traces for quadratic surfaces, and all of these. Okay, and then we have a lot more to talk about. Well, maybe I should say something like maxima and minima, because the now the codomain is R, or the range is a subset of R, so we can talk about the maximum value and the minimum values. And then there is another interesting thing that occurs in these multivariable functions, and these are called saddle points. Okay, so all of these are in this chapter. Okay, now we go to section 4.1. And by the way, I should warn you, because I want you to get really, really familiar with the fundamental ideas of these the real valued functions, but multivariable functions. The homework set is very large for this one particular section, 4.1. Okay, and in fact, I have over 30 homework questions, but I do want you to really pay attention and do all of these problems. You may struggle with some, which is fine, because again, remember, there's no pain, no gain. There's no learning unless you struggle a little bit. And so, okay, let me give you an example, right, of these. F of xy is equal to the first one. This sounds weird maybe, but negative 1/2 x minus 1/3 y plus 1. Okay, so let's see what this is. Okay, I think it's I think it's obvious that the domain is all of xy. Now, you can't any longer say the domain is a set of all real numbers, okay? Because now the domain consists of x and y. So this will be the entire R2, okay? Or you could say this is a set of all xy, where x and y belong to the set of real numbers. In other words, it's a set of ordered pairs. You can also call this the whole plane, okay? Because that's exactly what the set of all x, the ordered pairs x, y is. And that's because there is no restriction, right? You can put any x and any y in here and you can evaluate the function. Now notice here, z is negative 1/2 x minus 1/3 y plus 1. You can multiply everything by 6, for instance. This will be 2y here plus 6, okay? And it may look somewhat familiar. I hope it is. Okay, so what do you think this is? Okay, well, this is a surface you've seen before. In fact, there is no squares. It must be a plane, right? And so the graph is going to be the type of plane. And in fact, it's fairly easy to graph this function. Whoops, that is not what I wanted to do. Okay, so without thinking too much about this. And by the way, if you have to evaluate this at, x is equal to 6 and y is equal to 20 or something, you can easily plug in the numbers here, okay? And you can evaluate the function. That's probably the easiest type of functions or the questions you can ask for these multivariable functions. But what kind of a plane is this? Well, simply plug in some numbers in here. You can see 2, 0, 0 would satisfy this, right? And then how about the 0, 0, 1? Yeah, and 0, 0, 1 would satisfy this, and 0, 3, 0, you can easily find, because I made the numbers this way, you can easily find these intercepts, right? And then all you have to do is to connect these, and then you will see a part of the graph of this. Now, of course, this is a plane that continues on forever in all directions. So this is the entire plane, and that's the graph of this function, right? So you just keep extending this in all directions. Okay, you can tell that this has the normal vector, which is 3, 2, 6, right? Because that's how you can find a normal vector. It comes out directly, sort of straight at us, like it's hard to draw this, but it's sort of like, this way, comes straight at like our direction, and you can see the intercepts. So this is an example of a function of two variables. All right, let me see if I can give you another one, maybe two other ones. What happens if one is missing? Can you figure this out? Yeah, I think you can. And this time, because x is missing, it should be exactly the same as you cross this at any, any vertical line where x is constant. And so the idea is maybe you can just graph what this function is when x is equal to 0. The cosine function starts at 1 when when y is 0, z is the, the value of f starts at 1, and it goes down at pi over 2 to 0, and then -1, then comes back to this, and then goes up like this, right? And then keeps going, a periodic function. All right, so that's what the function looks like when x is equal to 0. And of course, because x is missing, you will continue to just sort of draw this, extend it in the x direction, both positive and negative x direction. Okay, so this will be, what do you call that? Sort of like a corrugated piece of metal or paper or something. And so this is like a wavy plate. A wavy, not a plane because it's not flat. Okay, a wavy plane, right? So I forgot to say, maybe you can figure out the range of the first one. What is the range of the first one? Well, x can be arbitrarily large or small, and so is y. I think you can see that range is the entire R, which is the open interval from -infinity to +infinity. This one here, do you see what the domain is? Okay, even though all you see is y, the notation here makes it clear that any x is okay too. So this is also R2, the entire plane. Okay, you can say the plane, the entire plane, that's the same thing. And then the range, well, this time it's the value of a cosine of something, namely y. So you know that it does not go below -1 and go above +1. So the range is rather restricted, and that's how you can, describe this motion. All right, let me give you another example. F of xy is equal to 9 minus x squared plus y squared. All right, so what's so relevant about this? Well, again, you can remember how to graph this. And I'm not going to spend a lot of time on this, but you can probably see what the graph is going to look like. Boom, there it is. Okay, so this is an upside down paraboloid, and you can tell that from this equation, right? All right, so this is a circular paraboloid. And what do you know about this? And by the way, this kind of goes on forever also, right? It doesn't stop at the xy plane. And the domain, is there anything that you should avoid in terms of x and y? No, again, any x and any y and any combination is allowed. So the domain is the entire plane. The range, this time you just happen to know because it's a nice circular paraboloid. It goes to negative infinity downward, right, as x and y become very large. But no matter what x and y are, it never goes above 9. And that's because x squared will be non-negative and y squared is always non-negative. And so the maximum it gets. And of course, you can say later that the absolute maximum value is 9 that occurs at the origin 0, 0. Okay, so this is the kind of things, it's not too difficult, right? We will investigate these things more. Okay, so the domain. Sometimes it's called the natural domain. Okay, it's basically R2, okay, except at points, and we'll be looking at these exception points, but except at xy where the function is undefined. And so what's undefined? Well, the negative in the square root set. Yeah, maybe I should mention this. So avoid, and there are some specific things to avoid. The first thing is a zero denominator. You all know how bad it is, zero denominator. Okay, you should avoid negative number inside of the radical sign, or cube root is okay, but the fourth root you shouldn't have negative numbers, and that's because we want to stay in the realm of the real numbers, not complex numbers with I. And also you should avoid 0 or negative numbers for log, including the natural log. And if you think about it, I mean there are a few other things you should consider, but most of these are just these, right? Avoid these, and you will be okay. So, for instance, if you have, so let me just give you an examples here. If you have x, f of x is x squared minus y squared, what's the domain? Okay, there's no reason to exclude any x or y. After all, we are very tolerant people, mathematicians are. We allow for every possibility unless something goes really bad, like undefined. So in this case, the domain is R2, right? So what happens if you have something like this? Okay, now we have to watch out, right? Because the domain is basically all of R2, except we can't have the zero denominator. So you have to exclude this line, y is equal to x, right? And we'll talk a little more about the boundary of a domain. Okay, what happens if you have something like 1 over the square root of x? Okay, so here, x plus y, right? So here, the thing is, so you want x plus y to be at least 0, and possibly greater than 0 is okay because it's under the square root. And so this means y is less than or equal to negative x, right? Okay, so that's it. But, well, it's not it. Okay, but also because this is in the denominator by itself, okay, you can't have this as 0. And so that means you don't want this to be equal to 0 either. Okay, so you have to avoid that y is not equal to negative x. So this will be the set of all points except for this line. This is the line y is equal to negative x, right? Well, actually that's not true. If y is greater than this, then it's okay. And so all of these points will be acceptable, except you can't have this, right? So these are the things that you have to remember when you think about the natural domain of these functions. Okay, so let's go into an example here. I am going to give you a definition of, I'm going to give you a function, okay, y minus x squared under the square root, right? I want you to find the domain, the range, I think you can find it, okay? And then we'll talk about the boundary. This is a sort of a new concept, the boundary of the domain. All right, so when you graph, oh yeah, and then you may want to graph this function here too. Well, I don't know, it may be hard. All right, and see if you can find the domain, the range, and the boundary of the domain. and then we'll come back.